Hello and welcome to this brief presentation related to examination preparation for our applied mathematics examination. This is the sample paper we reviewed in the lecture. I'll just put this video together to briefly outline our solutions, some of which we didn't complete within the lecture. There is a marking scheme available for the paper, but I very briefly tried to show you solutions that are fully worked through for your reference. Here's a very brief overview of the sample paper. Essentially contains 6 questions. Note that usually there are 7 questions in the exam papers. This presentation includes very detailed solutions to all the questions. There's far more detail than you actually need to state in the examination, but I've just tried to label the solutions to hopefully help you with your understanding as to the mathematical steps involved. Note for reference, there are previous lecture presentations to all of the following topics, which are required to attempt the questions in this sample paper. I'm going to let you review all the questions at your own pace. Essentially, I'm just going to show you the solutions. So here's question 1. Let you read this at your own pace. Question 1 continued. Part A here. Question 1. Here's the answers. Coordinates for hole B, hole C, and hole D. They're all determined from the dimensions shown in figure 1 here, which is not drawn to scale. Question 1 continued, part B, calculating the coordinates of point E, shown here in the diagram. To determine the coordinates of point E, shown here, I use holes A and B, and I average the X dimensions of these 2 points, and I average the Y dimensions of these 2 points. Calculations are shown on the following slide. Question 1 continued, part B, my first attempt at the solution. Here are the calculations for finding the dimensions for location E. I've referred to it as a hole E, but it's actually this position here on the plate. Question 1, part B, my second attempt at the solution, solving these simultaneous equations using the elimination process. Question 1 continued, part C, shown here. The simultaneous equations from part B are now expressed in matrix notation, given here. We've got to calculate the inverse matrix for part C, and for part D we've got to essentially solve for the unknowns, which are the values of X and Y. Full solution shown on the following slide. Question 1, part C continued. This was part D here. Here's question 2. I didn't work through this question in the lecture. The topic is on specific video. This is the video from our YouTube channel that contains a similar solution to this question. But here is the solution on the slide. Question 2, part A. Question 2 continue, part B, 1 and 2. Here's question 2, part C, solution. I'll let you review this at your own pace. And question 2, part D, full work solution. Again, I'll let you review this at your own pace. Of course, if you prefer, you could actually insert the values of alpha and theta at the beginning of the calculation. I've worked the solution through algebraically, so I first entered the values here. You could rework the solution by entering the values at the beginning. Here's question 3, electrical context question. We're required to solve the differential equation shown here. Question 3, part A solution. This is the solution we worked through in the lecture itself. Continues here. Here's question 3, part A, solution continued. Just for your reference, this is a slight variation on the solution we undertook within the lecture. The overall answer, of course, will be the same. Solving our differential equation. Notice I've written it on one line here. And I'll let you review the solution at your own pace. It's continued on the next slide. Question 3 part A solution continued, and I'll let you review this part of the solution at your own pace. Here's the final answer, what we were asked to prove. Question 3 part A solution continued. This is an alternative solution solving the integral from the previous slide, but now using a standard form shown here, function dash x divided by function of x. We've reviewed this standard form in our previous presentation related to integration using substitution. And essentially, if the numerator is the first differential of the denominator, we can simply write the solution as ln function of x. So with this example, v minus vc, if we differentiate this with respect to vc, we have a value of -1, but in the numerator we actually have +1. If we were now to make the numerator -1 and factor the denominator by -1, we would not affect the overall question, but now the numerator is the first differential of the denominator. So now if we write that within the integral sign shown here, but have a -1 outside of the integral in this case, in other words 1 divided by -1 is -1. When we integrate with respect to vc, we can simply write the solution down as ln of v minus vc, but the answer is negative due to the above process, which is essentially what we have here in our previous solution. Question 3 part B. Question 3, solution to part B. And question 3. Again, another version of the solution for part B. Here's question 4. It essentially relates to a projectile launched at an angle from the edge of a cliff, which is above sea level. I'll let you review the question at your own pace. Question 4, continued here. We're given our equation for height h of the projectile above sea level. So notice height h is a function of t in this case. Question 4, classroom solution. Again, another hint used here. This slide shows how to set up the quadratic equation. And here's question 4, part A, full solution shown here. This is part 1 of question A. Question 4a continues is part 2, hint in the question. Question 4a, part 2, here's a solution. Question 4, part B, question shown here. This is a hint to commence the solution. Question 4, part B, here's the full work solution. Question 4, part C, here's the question. I'll show you the full solution on the following slide. Question 4, part C, solution. I have to now find V0. Question 4 is the full work solution. Question 5, this is the question I left for you to work through at your own pace. Here's question 5, part A1. We essentially have to draw a graph given the information shown below in table 1. The graph shown on the following slide. Part A, item 1, here's the graph drawn from here. Question 5, part A, item 2, estimate a value from the graph. Question 5, part A, item 2, the estimate from the graph. Referring to our graph here, we'll have to find the time it takes to travel the last 150 meters. The total distance traveled was 300. Here's 150 meters, so there's still 150 meters to travel. So from the graph it takes 10.5 seconds to travel 150 meters. If the total time taken was 15 seconds, then that means the time taken to travel the last 150 meters is 4.5 seconds. Question 5, Part A, Item 3, require an equation of motion here. And for your reference, here's an extract from the formula sheet in the mathematics section that contains the equations of motion, or the Suvat equations, they're sometimes called. Question 5, Item 3, is our equation, is a solution. Question 5a, part 4. Again, it's basically an equation of motion. Solution shown on the following slide. Question 5, part 4. Solution. Question 5, part B. And I'll let you review this at your own pace. We're moving away from Newton's laws of motion to energy methods. Question 5, part B. Commencement of the solution. Review this at your own pace. And question 6. This relates to integration using volume of revolution, given the equation required in the question here. Solution shown on the following slides. Question 6, just slightly enlarged view here. We will need to replace y in this equation with the function of y given in the question for our curve between the limits of 1 and 2. Question 6, solution shown here. Essentially we're integrating a product with respect to x. So we use the integration by parts formula. Let you review the solution at your own pace. Continued on the next slide. Question 6, solution continued here. Final answer shown here, the volume. So that's the end of the presentation, which I hope has been of some use to you, and I wish you every success in the examination.